That's good.
Okay, well, first off, I'd just like to welcome Professor Pete Burgess, who's going to lecture tonight. Pete is a sedimentary geologist, a code developer, researcher, teacher, deals in sedimentology, sequence stratigraphy, basin analysis, and a lot of numerical forward modeling. And he's currently researching carbonate platform dynamics, siliciclastic delta cliniforms and shelves, sediment routing and stratal patterns on deep water fans. And he teaches at undergraduate, MSc, PhD, and industry courses, and is currently developing and delivering courses focused on the application of coding to various areas of earth science, which is an area I think a lot of people probably don't have exposure to, but it's a very powerful tool in modeling geological systems. So I would like to hand over to Pete, who's going to talk tonight. It's all relative, the ups, downs, tilting, and rebounds of ancient sea level. So just before Pete begins, could I just ask if everyone could turn off their video and mute themselves so we have the best bandwidth for Pete's talk, please? Thank you very much. Over to you, Pete.
Cool, thank you, Richard. Yeah, the coding thing actually, mostly at the moment, it seems to be making students' heads hurt. That's what I'm noticing. I think it's a bit of a geology students learning to write computer code is quite a challenge for some of them. I think it's not what they're used to. But anyway, sea level. This is what I'm going to talk about. Okay, I'm going to define what sea level actually is. So in a geological sense, as well as just the more general sense that we probably all understand it. Talk about why global sea level changes. Discuss how we determine or figure out or measure ancient sea level. And then following on from that, what is the history of global sea level change through geological time? And then finally, I'm going to talk about tilting continents, isostasy, and relative sea level change to bring in a more tectonic element to the discussion, which is particularly significant in the deep time history of sea level change. Okay, and I think I first did a version of this talk for a research talk actually in Houston, and I put in lots of pictures of cats in variously precarious situations. And I think it was just because that talk was quite mathematical, and I thought if I put the cats in, it'll help, ease people into the subject a little bit more. So I've kept them in here. There's some good ones. So if you see precarious looking cats, that's the reason why. Originally it was to make the maths a bit easier. So let's start, and there's one. Look, I mean, I don't know quite how that cat got into that position, but there you go. So first of all, a definition: what is sea level? And obviously there is a simple answer to that. It's the place, the elevation of the land where we can go and stand at the interface between land and sea. And here's a few examples of that, places that I've traveled to. Oh, blimey, remember when we could travel? It seems like a long time ago. So this is a fairly local place, Blundell Sands, Liverpool, where Anthony Gormley's statues are, which are a pretty good marker actually of how sea level changes on a daily basis, right? You can watch them go be exposed and flooded in the tide. Santa Monica, California is one of my favorite places, a lovely place to paddle. Bar Al Hikma, Oman, I used to take colleagues there from Shell on field classes, and Rio de Janeiro is an interesting place. It's, you can see sea levels here, but there's also, I think, a very interesting tectonic history there of uplift and erosion, but we'll come back to that. So basically, sea level, it's a place where you can go and you can paddle. Okay, that would be the simple definition. But when we look into it a bit more and we start looking back in, I mean, not necessarily into deep time, but we look back into history and deep time. And even when we actually go around the world and look at different locations that are in different tectonic regimes, we start to see that perhaps it's a little bit more complicated. So in Death Valley, that's where this is, you're instructed to park off the pavement. You can also take your picture at elevation sea level. Well, clearly, if you look behind, that's actually the Californian desert. So it is below sea level, but it's certainly not flooded by the sea. So we're quite a way inland here. So this is demonstrating that the surface of the Earth obviously is not a uniform sphere, and it's certainly, you know, one place. There are several places on the continents that are substantially below sea level, but actually not flooded by the sea. And then this location is Herculaneum near Naples. And the significance of this is that sort of row of arches there was at sea level during the time of the eruption of Vesuvius in AD 49, I think, and now quite clearly it isn't, and I'll talk again about that in a second. And then there's a couple of pictures here of rocks that actually mark the ancient position of sea level. This one's in South Wales, where lower Jurassic strata onlap onto Carboniferous limestone beneath, and you can basically see points where the layering of the Jurassic limestone pinches out against the Carboniferous limestone. That was probably pretty close to sea level back in lower or early Jurassic times. And there's a similar, slightly more complicated surface here where upper Miocene rocks onlap against, I think, probably upper Paleozoic schists. This is in southern Spain in a place near Carboneras. So we see places in the rock record that also record the position of sea level. And looking at these four pictures, you start to get a sense that it is a bit more complicated than just, you know, the place where you can paddle. So let's talk about Herculaneum for a second then, because this is an interesting story. This is paleo sea level, but not very paleo. It's only AD 79. So actually, geologically, that's nothing, right? Historically, it's a while ago. And sea level, or the coastline now, at least we should say, is a kilometre or so, I think, further west from this position. And that's mostly because the eruptions of Vesuvius deposited large amounts of ash and so on that basically built up the land surface, built it out, and effectively raised the area here above sea level, buried most of Herculaneum. So the position of the coastline changed quite dramatically, okay? But that's not quite the same thing as saying that sea level changed, right? So again, the land surface can build out, and the apparent, well, the position of this of the land sea interface changes, but that's not necessarily the same thing as sea level changing, okay? So there's quite a few things going on here, and what we therefore need to do is be a little bit careful about how we define what sea level actually is. So let's talk about a couple of definitions now. So eustasy is a very useful word to understand when we're talking about sea level, modern sea level in deep time history. So eustasy is any uniformly global change of sea level that may reflect a change in the quantity of water in the ocean, or a change in the shape and capacity of the ocean basins, or put in simpler terms, a change in eustatic or global sea level. That's what eustasy is. So we're talking about global sea level, the elevation of a more or less uniform sea surface around the planet, okay? And the way it's typically depicted is with diagrams like this, where you've got essentially a circle going around, you know, part of a spherical Earth, and eustasy is defined as the distance of that sea surface from a datum which is taken to be the center of the planet, right? That's how we define global sea level, but against that global datum, the center of the Earth. But we also have other things shown on this diagram, right? We've got water depth, we've got relative sea level, and relative sea level, I'm going to now go on and explain, and it's a little bit of a different thing. It's kind of related to eustasy and global sea level, but it's slightly different in how it's defined. And it'll start to come back to some of these points I just made about, you know, the coastline moving and places like Death Valley, which are below sea level, but, not flooded and so on, right? So, relative sea level then, so we've got a new diagram now here showing a cross section. And this is a cross section that could be through something like this. This is the Lena River Delta in Siberia. I picked it out because it's just such a beautiful image of a sort of bird's foot type delta, right? Building out from a river that's flowing north into the Arctic Ocean. And this is a cross section through it. And so basically we've got the top of the delta here, and then where the delta meets the sea, it slopes down into deeper and deeper water. This is what we call a cliniform. Okay, so this is a cliniform surface. And if you walked off the front of the delta there, you would basically be walking down this surface here, all right? And so we can think about how underneath a system like this, we would use that cross section to define sea level. And basically, global sea level is drawn the same way as it was on the previous diagram. The elevation difference between this sea surface and the fixed global the center of the Earth, right? Not to scale, obviously, that would be way off the bottom of the slide if we drew it to scale, right? But you get the idea that this is Eustacy. We can also define something else really useful, and that is relative sea level, and that's the elevation or the height difference between the sea surface and some local datum. Okay, so that is typically taken to be, for example, the top of basement rocks. So underneath some defined sediment pile where we go down into crystalline rocks underneath. And that's quite a useful tectonic marker surface, right? Because as you accumulate sediment, you can actually see on seismic data and so on, and I'll show you some examples of that in a while. You can see this surface kind of, you can usually map it out and work out how thick the sediment is and use it to define a relative sea level height. Okay, so now we've got global sea level, which is the height of the sea surface relative to the fixed global datum at the center of the Earth. And we've got relative sea level, which is the height of the elevation of the sea surface relative to some local datum, whatever we choose it to be, but top of crystalline basement rocks, for example, okay? And the reason this is so useful is because if we have tectonic processes that act, so for example, here's the diagram modified to show a very simple vertical fault with a down thrown side here. If we actually down throw that fault and actually drop this block of basement rock and the sediment overlying it with it, we effectively increase the distance between that local datum and the sea surface. And that actually then is a rise in relative sea level. If we were sitting down on the seafloor there, when this fault went down on this side, what we would experience is a relative sea level rise. We would see that the distance up to the sea surface from where we were sitting would increase. That's rising relative sea level. Okay, so this is a really useful way to think about sea level change as well. It's not global anymore. It's not going up and down globally, and we'll come back to how that works shortly. Now we're talking about just local relative sea level changes because of things like active tectonics. Okay, so it's good to have got those definitions in place, and maybe now you can start to see that some of the effects I was talking about before, some of the examples, places like Death Valley and Herculaneum, maybe there's some more of these kind of effects going on. The coastline perhaps is changing place because of deltas building out or some volcanic equivalent ash flows or whatever. And if you've got faulting, you can drop a block of basement rock and actually cause what appears to be, what is a relative sea level rise because of that tectonic downthrowing or subsidence. Okay. And here's just a quick definition then of what tectonic means, in case you're wondering. I mean, I like definitions. I think they're really useful. And in fact, I think Clive Bolter's watching this, you were the first person who ever actually explained to me what the distinction was, Clive, between tectonic and structural geology. I remember asking you this question when I don't know whether it's in a class or whatever, and you explained. It always puzzled me what the distinction was, but actually tectonics then is processes, basically anything concerned with the structure of the crust of a planet, but particularly the processes that form folds, faults, deformation of rocks generally, right? That's tectonics. So when we talk about tectonic processes influencing sea level, we're talking about how the plates and deformation of rock masses then impacts on the elevation and local or relative sea level. Okay, and I'll come back to this in a bit. And in case you're wondering, this is my, I think probably my favorite picture of tectonics. This is I think it's Millock Haven. Is it Millock? I can't remember the name of the place now. I'm having a total mind blank. Oh, I'll think about it. You ask me at the end if you want to know where it is. It's in Cornwall, basically. Go on.
It is Millock Haven.
Is in Millock Haven. Good. I was thinking I was getting it confused with somewhere else, but Millock Haven. So this is a fantastic example of tectonics, right? I mean, one of the best. Okay, but it kind of explains how that definition really, works in practical terms. And this diagram I'll explain in a little while why that is relevant to us. Okay, so now that we've explained the difference between well, we've explained what relative sea level is, we've explained what global sea level is. Let me just tell you a little bit more about how relative sea level works, right? So if we add together two different effects, we add together a global sea level curve like this, and I'll explain what this means, right? We've got time on the x-axis in millions of years. We've got 2.5 million years there, and we've got sea level elevation on the vertical axis. So what we're seeing here is a long-term 500,000 year rise in global sea level, then 1 million years of global sea level falling, and then another 1 million years of it rising again in a sinusoidal type pattern. Okay, and you can see that superimposed on that longer term, there are these shorter term fluctuations, which is slightly lower in amplitude, but significant enough that you can see them. So you've got a low frequency, long wavelength effect, which is causing this oscillation, and then you've got this high frequency effect that's causing these much shorter term oscillations. And this is how we think a lot of global sea level change works in deep time Earth history, right? And again, I'll talk more about this as we go along. Now, if we combine that with steady subsidence, right? And lots of parts of the Earth's surface undergo subsidence. Sedimentary basins are the prime example, right? What you can do is add those two effects together to define a relative sea level curve. So if you think back to one of those previous diagrams where I showed the fault dropping and that rising relative sea level. So what you're effectively doing there is adding together the eustatic sea level component. So if that changes, you add it to the subsidence and you get your relative sea level curve, right? So this is the relative sea level curve, is kind of the effect that the rocks would experience and record. So if you see patterns in rocks that are related to sea level change, it's relative sea level change that they are recording, a combination of subsidence or uplift and changes in global sea level. So you add the two things together and you get a curve like this. And you can see that there's a steady rise in the relative sea level from here to here. There's a rise, but you can see that there's a fall in there, which is caused by the global sea level fall here. So you're basically adding the two things together and getting this pattern of relative sea level change. Okay. All right. Now, just to come back and clarify the point I made about Herculaneum, not all movements in the shoreline, though, are going to be due to sea level change. Some will be, but not all of them, because here in this particular case, imagine this delta builds out because rivers, or the river that feeds it, feeds lots and lots of sediment in, and over thousands, tens of thousands, hundreds of thousands of years, it builds out into the Arctic Ocean. In cross section, it's going to look something like this. And even if there was no sea level change, eustatic or relative, this coastline would build out, right? Just because of the sediment supply that was coming from the river, right? So coastlines moving, migrating, is not in and of itself necessarily a consequence or evidence for sea level change. It can happen regardless, all right? But onto the next diagram, it can also happen in combination with sea level change. So in this particular diagram, the shoreline starts off here, and after some specified amount of time, it would be here, both because you've built the shoreline out because of this sediment supply, you know, the delta building out seawards, and also because you've had relative sea level rise. And given that we've got no differential subsidence here or anything like that, or any faulting, perhaps that would also be global sea level rise. Okay, it could be subsidence, or it could be global sea level rise, or some combination of the two. So now you're adding together several different things to give you this movement of the shoreline. Okay, and it starts to get a little bit more complicated, because if you consider it, if you were just looking at that in an ancient rock example, it's actually quite hard to decipher which of the particular effects has happened. There must have been some building out of sediment here, but quite how much subsidence versus global sea level rise there has been is actually quite hard to unravel. And we'll come back to this point a little bit later. Okay. So definitions then, let's just finish this off. Sea level is marked by the place where we can paddle. It's the place where the sea meets the land. Bit more complicated in geological time because the shoreline position can also change without any change in sea level just because of sedimentation. And the exact way we define sea level is quite, I wouldn't say complicated, but more complicated than you might first think, because there's eustatic sea level and there's relative sea level, okay? And they're different things, but, you know, related. So what causes global and what causes relative sea level to change? Let's talk about the mechanisms. So there's two main things. We can categorize the different mechanisms into two different categories. There's climate control and there's tectonic control. All right, let's talk about the climate control effects first. So if the temperature of the oceans changes, that will change sea level. And the reason is because the water body, when it changes temperature, either contracts as it cools or expands as it heats up. Okay, and this is a rate of change, centimeters to a few meters change over hundreds to thousands of years. Now, so far, because of anthropogenic global warming, most of the sea level change that we observe is because of this effect, right? So far as scientists can determine anyway. Okay, and I'll show you some curves that show that shortly, right? So seawater temperature is one way that we can change global sea level. Now we're talking about global sea level. We can also change global sea level by taking some of the water that's stored on continents, putting it into the sea, the oceans, or vice versa, right? But the volumes of those water stores are not huge. So the rates of change related to that process, we think, are quite low. Okay, it's not a particularly fast process, and probably not a huge magnitude change. Even if we took all of the water that's in the continents and put it in the sea, I don't think it would make it a really, really big sea level change. But, you know, estimates vary. The thing that we do know would make a big difference is ice caps. So the continental ice caps, when they melt, they raise sea level quite dramatically. And here are some of the numbers related to that. So probably the easiest one to visualize there is the Greenland Ice Sheet. You know, you all know Greenland and you know approximately how big it is, where it is in the world and so on. You know, it's quite a big area of land covered in ice currently, and we know that that ice is melting and probably melting increasingly rapidly. If it all melts, we get about 7.3 meters of global sea level change, right? And this is one of the reasons why anthropogenic global warming is such a problem, or will be increasingly more and more of a problem for us. That effect, 7.3 meters of sea level change, would drown most coastal cities. It will be very difficult. It's going to be very difficult for them to you know, continue with a business as usual type approach when sea level rises by that much. So if we do lose these ice sheets, we're in trouble, basically. There's going to be a lot of work to try and fix this problem. And the Greenland Ice Sheet is similar kind of size to the West Antarctic Ice Sheet. Both of those we think are probably quite unstable as the climate warms up. The East Antarctic ice sheet, that's unlikely to all melt quickly because it's a big, big ice sheet and it seems to be pretty stable. But if it does melt eventually, we're talking about all of these things together gives us about 65 meters of sea level change. Now, I don't know about you, but I kind of go around cities now and look at them and think, how much of this city is above is you know, more than 10 meters above sea level or more than 5 meters above sea level? If you stop and think about this, this is going to cause total carnage if this ice really does melt in the sort of way that some of the worst case scenarios predict. Now, in deep time, we know that this has happened in the past because we can find the traces of continental ice sheets melting and driving big global sea level changes. They happen probably a bit more slowly than this might happen and in a different way. But we know that, you know, ice sheets do melt like this. And of course, in the past, they've also formed, you know, over time. And when they form, when an ice sheet forms, it actually lowers sea level because it takes water from the oceans and stores it on land. So this process can work either way in geological history. In the human future, it's very probably only going to work one way, that's with melting, right? But continental ice caps then are a really major component of global sea level change. And just to mention very, very briefly, what drives or what has driven that process of global ice sheet growth and melting over the past couple of million years is Milankovitch cycles or variations in the Earth's orbit that in turn control the amount of radiation that hits the Earth's surface. And that's to do with basically a few different effects in the Earth's orbit. The eccentricity of the Earth's orbit around the sun is how circular versus elliptical it is, and that controls the overall distance from the sun on average, or how it varies over time. That has a big impact on, well, actually, it has a small impact on global temperature, but that's then amplified by various other processes that can drive cycles of ice sheet growth and melting, right? And we kind of know from the last couple of million years that that's what's happened. Okay, they've got particular timescales of periodicity that these different changes in the orbital parameters occur. Okay, and we can identify some of that periodicity in rocks and ice cores and such like from deep time. So this is all related still to ice volume changes. Okay, so those were the climatic mechanisms. So we had water storage on land, we had ocean temperatures, and we had ice volumes. There's another class of controls that are essentially tectonic. And the big difference, aside from tectonic versus climate, the tectonic ones tend to be much slower acting, but they make a big difference over long time scales, right? So one of the key things that affects global sea level, a tectonic mechanism that affects global sea level over long periods of time is the state of the spreading centers or the ocean ridges that mark constructive plate margins, right? If those ridges are fast spreading relatively now, then they tend to be shallower, more elevated under the ocean surface, and therefore actually the ocean basin that they're in tends to be smaller volume because the crust underneath the ocean basin is more elevated because the spreading is fast, hotter asthenosphere nearer the surface, all that kind of thing, more buoyant. And water then gets displaced onto the continents as a consequence. With slow spreading ocean ridges, you've basically got a deeper ridge crest, a larger ocean basin volume, and we've got therefore lower global sea level because the ocean basin volume is greater. There's more storage capacity for the water, less water displaced onto the continents, lower global sea level. Okay, and there's just a ridge bathymetry. I think that's down that's the North Atlantic down into the Central Atlantic and South Atlantic, and you can see the ocean ridge there, an elevated mountain chain effectively. That's this. And I think the Atlantic is not super fast, but it's not slow either. It's kind of in between. Okay. So spreading rate is a key control, but it's actually quite complicated, and we're sort of learning more and more about exactly how it works. And these are from diagrams from a 2006 paper that essentially try and estimate spreading rates, ridge volumes, the flux of ocean crust generation through time, and relate that back to a time scale and to sea level changes. Okay, and so that's, and it's a bit complicated because doing those reconstructions can be a bit complicated. So trying to figure out exactly how this happened in the past is a little bit tricky. It can be computed in different ways, which is what some of these different lines on the graphs are showing you. Okay, but basically the flux of ridge production changes. So this rate of this flux is basically whether it's fast spreading or slower spreading, and you can see that that's changed through time for various different ridge systems. Okay, and that then affects global sea level. Okay, so the other big tectonic control on global sea level is actually the age, the thermal age, since it was formed at a spreading center of oceanic lithosphere. So if you look at this is a beautiful map, actually. I really love this map. It's a bit, maybe a slightly garish color scheme, but it shows such a fantastic relationship. The red is basically young oceanic lithosphere. The blue is the oldest oceanic lithosphere, and you can see green, yellow in between. So obviously you've got the youngest rocks formed just at the spreading center. And over here in the Western Pacific, we've got really old Jurassic oceanic lithosphere. It's, you know, it's very, some of the old, well, the oldest oceanic lithosphere on the planet. It's about to be subducted over here. But basically, because it's old, it's also cold, right? It's had lots and lots of time, almost 200 million years in this case, to actually cool from being a hot ridge oceanic lithosphere to a deep abyssal plain oceanic lithosphere, much older, colder, denser, right? So it's deeper. So how much old versus young lithosphere you've got in the ocean basins affects their volume. An ocean basin that was full of really old, cold oceanic lithosphere would be deep, lots of water volume. Ocean basin that was full of ridges and not much else, you know, really young lithosphere would be much shallower and would displace water onto the continents because it would have lower volume. So this is a long-term tectonic control on sea level. Okay, and here's basically some reconstructions of that. So what people are now doing is building digital plate models back through time that try and reconstruct some of these processes to try and understand, for a given kind of distribution of plates and oceanic lithosphere, what sea level would likely have been given the reconstruction of ocean basin volume. Right, so we're starting to understand this now a lot better. We've kind of known that this happened for a long time, but with these kind of digital plate models, we can really begin to explore what the consequences are of different scenarios for spreading evolution and so on, and understand what impact that would have on ocean basin volume and Eustacy. Okay, so those are two plate lithospheric related tectonic processes, but there's another thing as well that goes on. Okay, so tectonics is not just about the plates in the Earth's crust and lithosphere, it's also about what happens deeper in the Earth. And deeper in the Earth, we've got the asthenosphere and the deeper mantle, and essentially they convect, right? So we've got heat from the core, it drives convection cells. There seems to be a distinction between convection in the lower mantle and the upper mantle. They seem to operate as different systems, different viscosities, different structures, compositions probably, and but basically convecting. Okay, and that convection has an influence on the Earth's surface, actually, because places where you've got rising buoyant plumes of upwardly convecting mantle rock hit the base of the lithosphere and force it upwards. It's like having a spot almost, or, you know, probably not a very nice analog to think about, but you kind of know what I mean. Another way to think about it would be in a pan of boiling water or soup. You can see the way that the hot plumes coming up from the base of the pan hit the surface and raise the surface of the soup or the water, exactly the same thing seems to happen on the Earth's surface in response to this mantle convection. And we call this dynamic topography. Now, if you displace the Earth's surface, that is going to be felt as a relative sea level change. So deep Earth mantle convection can drive relative sea level change of the type that we've basically just been talking about. Okay, so that's another tectonic process. This is dynamic topography as it is estimated to be. It's a little bit complicated to work out how it actually works. What it actually is, it's difficult to measure directly, is basically the issue. But this is our best calculations currently of what dynamic topography looks like over the surface of the Earth. So you can see we've got 2,000 meters elevation to minus 2,000 meters elevation from this red to blue. That's the kind of scale of change we're talking about, right? So this dynamic topography effect has a big change a big effect on the elevation of the Earth's surface, and therefore on ocean basin volume and on relative sea level as well. And I'll come back and talk about the consequences of this a little bit later. Okay, so I'll skip over this one. So just to summarize that bit then, global sea level change driven by climate and tectonic processes. Processes use static change. It's either varying the volume of water in the ocean basins or the volume of the ocean basins themselves. Tectonic processes are slower, but they can range in scale from a single fault moving to this dynamic topography effect that causes uplift and subsidence relative sea level changes over thousands of kilometers. So that brings us to the next question then. How can we extract a history of this relative sea level change from the geological record? We know those processes happen and have happened. What we want to try and understand is how exactly have they happened, where have they happened, when, and so on. How do we actually get that record out of rocks? So how do we determine ancient sea level? And here is another slightly I don't know whether that's cat's actually stuck or just having fun. Actually, it doesn't look as unhappy as some of the other ones do. Okay, so global sea level then, we have been measuring it directly, okay, for the last 100 years or so, and by two mechanisms, either by using tide gauge data, which is a slightly messy data source because you have to do some adjustments for sort of local conditions. And more recently, in the last 30 or so years, by satellite radar altimetry, which measures the sea surface directly. You have satellites in fixed orbit. They bounce radar signals off the sea surface, and you get a very, very detailed, accurate measurement of sea level change through time. And you can see those things have given us this sea level curve, which you can break into a series of straight lines, which give these kind of rates. So in the early part of the 20th century, it was 0.6 millimeters per year. Now it's about 3.1 millimeters per year. So, I don't know whether anybody gets involved in the arguments about is climate changing and everything. Well, yes, it absolutely definitely is. Sea level is changing as a consequence of that. Here's things that have directly been measured to actually show that effect happening. And this is worrying. I think the fact that the rate of rise of global sea level is increasing, and we'll come back to this in a little while, right? But the interesting question to ask is, how do these rates compare with sea level change in deep time? Because we've talked a little bit about the processes, and I'm saying to you that we're going to now talk about how we actually measure it from the rock record. So what kind of rates do we get? So I mentioned this briefly already, right? We can reconstruct sea level history by looking at sedimentary rocks. It's one of the ways that we do it, and I'm going to talk about another couple of ways that we do it. But in outcrops of sedimentary rocks, we can reconstruct sea level history. So the Lower Cretaceous Campanian rocks in Utah, this is a place where loads of work has been done on trying to reconstruct the sea level history that's recorded in these rocks. My particular favorite place, though, I think, is this early Jurassic example in South Wales, not far from Cardiff, actually. It's an absolutely wonderful outcrop, because you can do this. You can basically say, well, here are the lines, the bedding surfaces through the Jurassic limestone, and you can see them terminating or pinching out against what would have been an old topographic surface on top of the folded and deformed Carboniferous limestone. It had all been upthrust in the Riskin orogeny and then eroded. And then a long time later, Triassic and Jurassic times, sea levels gradually rose, or this area subsided. So it was probably a relative sea level rise, not necessarily just a global sea level rise. And essentially this old land surface formed of Carboniferous limestone in the early Jurassic then got progressively flooded. So this was a position of the shoreline, this was a position of the shoreline. And so we can reconstruct the relative sea level history from this pattern, which we refer to as onlap. Okay, you can see that progressively the strata get more and more landward and onlap or lap onto this topographic surface. All right, so this is marking sea level through geological time. You can measure the height differences here. That gives you an indication of sea level change. And it's always difficult reconstructing the time in detail because, you know, but the ammonite biostratigraphy in these rocks is pretty much as good as it gets. So we can have a reasonably detailed estimate of how long a duration of time these rock units represent, you know, probably in the order of, I think, 1 million years or so. And so from that, we can start to get rates of sea level change. Now, on a bigger scale, we can also use seismic images to do something pretty similar. All right, so I don't know whether you're familiar with seismic data, but this is like an ultrasound scan of the Earth's interior, the top few kilometers of the Earth's crust. You shoot sound energy down into the ground and you record how long it takes to be reflected back to the surface, and you do lots and lots of clever geophysics. There was a time when this computer power required to make these images was second only to the computer power required by, you know, nation states to spy on each other, basically. So it was the second largest use of computer power on the planet. I think it's been overtaken probably now by Facebook and such, but it was a lot of computer power. And oil companies particularly use this to look for oil and gas, but one spin-off was that we have images like this from which we can reconstruct sea level history. And if you look carefully, you might spot that in here there's a similar pattern to the one that we just saw on that Jurassic coastline of onlap, and we can mark those positions of onlap. There's another example just below. There's the one that I just pointed to, and those yellow dots are essentially sea level positions. I mean, that's a slight simplification. It's a bit more complicated than that in this particular case for various reasons that I won't go into, but it gives us an estimate, at least, of the sea level, the relative sea level history in this particular basin. And I don't even remember where this image came from, but, you know, wherever it is. This one is off the coast of Norway, I think. So I've shown this river delta example again. Remember the cliniforms underneath the Lena delta? Here's an actual example that's not just one of my cartoons from the Norwegian shelf. So you can see these cliniforms where they go from being flat to dipping. So that's the equivalent of this to this transition. Those yellow dots, again, they mark the position of sea level at some point in deep geological time. I think in this case, only a few million years ago, so not that long ago, you know, geologically. But we can reconstruct the sea level history. We can see that the coastline built out and then it began to transgress, and relative sea level rose faster than the sediment could be supplied. So this is a combination of sediment building out and then being overtaken by a rate of relative sea level rise. Okay, so this is kind of some of the effects that we were talking about to begin with, all combined and shown in one seismic section. I've said offshore Namibia, Neogean. I think it is actually offshore Norway. So there you go. They both begin with N, so that's not completely wrong. And here's a final example from a delta. This is offshore Mozambique, and this is a beautiful seismic section. The quality is not brilliant, but it shows a huge delta system which is recorded and has been there pretty much since the Cretaceous, and is recording cycles of sea level change. These yellow lines are showing the shoreline progression, and they look as though they're in a funny orientation, but it's because all the sediment's been squashed by what's basically overlying it. So they've been slightly deformed by that compaction effect. But we can reconstruct periods of delta growth and sea level and building out and sea level change from seismic sections like this. And we can do the same kind of thing from reefs, limestone reefs or carbonate platforms. And here's a beautiful example shown in a satellite image. This is the Caicos Islands in British West Indies. You can see a shallow lagoon. The red, I think, is land above sea level. And you can see deep ocean in dark blue off the edges of the carbonate platform. So the carbonate platform outline is like this. And in cross section, it looks like this. You can see lots of layers of limestone that's accumulated over time to build up this flat top. The platform is then drowned. So at some point, relative sea level rises outpace the rate at which the limestone can accumulate, and it's drowned. And you have this beautifully preserved isolated carbonate platform just sitting buried beneath lots of probably deltaic strata. This is offshore Malaysia. And in fact, lots of these isolated carbonate platforms are gas fields. There's lots of natural gas trapped in these rocks, which is why we've got such nice seismic images of them. But the point here is that you can track sea level through this layering of rocks, because these layers that are reflected in the seismic data, those are actually built up at very near to sea level, right? So every time you see one of those reflection surfaces in there, you can say that was a paleo sea level surface within a few meters probably. Okay, so that's pretty accurate by geological standards, right? It's not often that we can say we can measure things geologically to within a few meters. I mean, that's not precise for a physicist, but it's precise for a geologist, I think. Okay, so those kind of flat layers inside carbonate platforms give you a record of sea level. And we can also actually use something similar to, we can look at the way carbonate platforms build out through time. So here's an absolutely beautiful example from Gorontalo Bay, North Sulawesi. In this case, a carbonate platform builds out. You can see all the sort of cliniforms here, that same kind of pattern where you've got a flat surface at sea level and then a slope down into the sea. That marks the edge of one of these carbonate platforms. It built out through time, got a bit tilted, stepped back, kind of aggraded vertically for a while. So just built up vertically, jumped back, prograded a bit, jumped back, prograded a bit. The point is actually quite a complex history of the platform building out, retreating, building out, retreating. And this all records the sea level history in this area of Southeast Asia through the Neogene, right? So the past 20, 30 million years or so, okay? Amazing images. The thing that's really interesting about Gorontalo Bay, though, is not just that there's global sea level change at the time, there probably was, but you can see the fact that all of these layers were originally horizontal, and now, even though this is only probably 10, 20 million years old, it's tilted. There's been a lot of tectonics going on here as well. This whole area is tectonically very active. So the record of that tilting is also recorded in the rocks as part of the sort of relative sea level history, okay? All right, and so those are the sort of imaging and seismic imaging and outcrop methods to reconstruct sea level. We can also reconstruct sea level history from oxygen isotopes. This is geochemistry. I sort of use a bit because I have to as a tool. Sometimes it's not really my cup of tea. If any of you are into geochemistry, you can probably have talks from geochemists from time to time, but I'm definitely not one of those. But essentially, oxygen isotopes, the ratio of different oxygen isotopes in seawater changes through time, and it's a proxy for temperature, for water temperature. And that is therefore a proxy for ice volume and climate and sea level. And so we can reconstruct sea level history from that oxygen isotope record. Okay, that's that's the theory anyway. I think it's probably a bit more complicated than it's often presented in some of these research papers, because there are other things going on which I think people assume sometimes are not happening but maybe are. But anyway, it's another way that we can reconstruct sea level history through deep geological time. And then finally, a technique that I have used, and it looks a lot more complicated than it is, there's something called backstripping analysis, whereby you basically take layers of sedimentary rock, strip them off, sort of uplift the layers underneath to account for the fact that they've been squashed by the layers over the top that you've just removed. That is what we refer to as backstripping. And the point of it, without going into any more detail, is that we can reconstruct the history of subsidence and global sea level change from that process, right? So we've got several ways we can reconstruct sea level history from deep time records. We've got coastal onlap, which we can see in outcrops or seismically imaged strata. We've got oxygen isotopes and backstripping, right, which we can also use to actually measure, determine ancient sea level, right? Now, all of these methods contain substantial uncertainty because we're trying to reconstruct something that is a combination of several different effects, and that makes it a little bit complicated. Complicated basically means uncertain. So we have to be a little bit cautious with how we interpret some of the results of these reconstructions of deep time sea level history. Now, with that in mind, let's go and have a look at what they actually look like. What do those records of sea level through geological time actually look like? This cat, I think, is actually stuck between the windows here. I think it's got caught in the sliding doors, which, yeah, I mean, it looks quite worried, doesn't it? And I can see why. So anyway, if you are feeling like you're a bit overwhelmed with the details of sea level change, just think you're probably still happier than this cat was at this point. Okay, so sea level history through geological time. The way that that has been captured is as global sea level curves, right? And probably the first and most famous of these was produced by this chap, Bill Al-Haq, back in the late 1980s. And he used coastal onlap, which is that outcrop and seismic feature that I showed you, to reconstruct sea level back through geological time. Okay, so he's basically got this curve here. So geological time is on the x-axis here, and you can see that's the Paleocene. There's a Cretaceous Paleocene boundary is there. So dinosaurs here, no dinosaurs here, unless you count birds, of course, which in fairness, we really should. Anyway, no, lots of non-avian dinosaurs there and no non-avian dinosaurs there. And coastal onlap varying all the way through the Cenozoic according to Bill Al-Haq's measurements. And from that, he has reconstructed the global sea level curve, right? Okay, all very good. Here's some other variations on that same process, using slightly different methods but related, lots of onlap analysis, some oxygen isotope data, some backstripping, and these are the different sea level curves that people have come up with. Okay, now the thing that strikes me about those curves is they are all quite a lot different, right? That is not, to me, a consensus about what geological history of sea level variation is over the last 500 million years in this case, right? Some people are saying it was 400 meters higher in the late Cretaceous. Other people are saying it was 50 meters higher. There's a lot of difference in there, okay? And this is the point I was making about the uncertainty, right? If we are completely honest, I think we would say we don't really know a huge amount about how much sea level has changed or exactly how it has changed through geological time. Probably some of these curves we can say are more reliable than others. This purple one here, for example, the method that's used to reconstruct that, I think is probably a lot more reliable than this curve here because the method is much more robust, basically. Okay, so Bill Al-Haq was the first, but I think he didn't do a particularly brilliant job, if I'm honest, and other people have done better jobs since, but we're pretty uncertain. that one that I just mentioned, the one that I think is a better job, is a bit more realistic. That's the curve but from Ken Miller's group in Rutgers University in the US, and they use basically oxygen isotopes and backstripping, and they get a curve that shows some interesting features. It doesn't vary through time nearly as much as the HAT curve does. We're only looking at about 50 meters of sea level oscillations through most of geological time, apart from the last 5 million years or so, when you see this effect kicking in and sea level is dropping down to about minus 100 meters, and we're getting these big changes. You can see the red line here is changing, but it's changing much more rapidly here. Okay, so this is the effect of ice sheets growing in the northern hemisphere, melting, reforming, really quite big sea level changes up to the present time, right? So this is the onset of glaciation ice ages, or the present ice age that we are now, it seems, rapidly coming out of. That's recorded in this sea level curve, right? So this is probably the state of the art, the best representation we have, but still the measurements of sea level history back then, still pretty uncertain. We're not really, you couldn't really look at that and say that absolutely nails the sea level history without some significant amount of uncertainty. And people are now starting to use plate models, as I mentioned, to try and reconstruct this. So we're starting to bring together several different methods to try and refine how this all works. But you can still see, I mean, that's like a, you know, I don't know what the collective noun for complicated curves is, but it's a bit of a mess of curves is how I see it. So hopefully over time that will be resolved and it'll begin to, you know, look a bit more like one better defined sea level history through time. And just very quickly, this is some work I did with a colleague over the last few years. It's also starting to get a lot more quantitative, this reconstruction of sea level history. When Bilal Haq made his diagram, it was a bit, you know, it was a bit of a cartoon, basically. He went around ExxonMobil, apparently, asking people for their view of what the sea level history was in their particular basin of a particular age, and then drawing it on a piece of paper. Now we use, you know, more complicated, I would argue more sophisticated methods to try and reconstruct what sea level history is doing by combining the various different controls, subsidence, sediment supply, Eustacy, looking at them in what we call parameter spaces and taking a probabilistic approach. I won't explain what this is, but basically that big green square there, that's where it's most likely that you would find that those are the most likely rates of change of the processes that drive sea level change from our analysis of various data. Okay, so this is all about probabilities, but I think it's a more robust approach than simply drawing squiggles on a piece of paper and saying that's sea level. Okay, so just one final point about this curve then. The fastest recent rate of global sea level rise is this 3.1 millimeters per year. Okay, so that's 31 meters in 10,000 years. And that's quite a bit faster, I think, than the long-term rates of change that we observe through geological time from some of these previous sea level curves. But remember, they're actually quite uncertain, right? So modern observed rates are much faster than the long-term deep time rates, so far as we can tell. Okay, and there's some uncertainty, so maybe that view will change slightly, but I doubt it'll change substantially. But the really interesting thing is this 3.1 millimeters per year and those deep time rates are nowhere near as fast as what happened over the last 20 to 10,000 years ago. That was when big ice sheets in the Northern Hemisphere were melting. Okay, so the North American ice sheet, the North European ice sheet, and that drove sea level rise of about 125 meters over 10,000 years, right? And that's quite a lot faster even than we're seeing currently. So what we know is when ice sheets melt, they can melt quickly. And when they melt quickly, they drive very rapid sea level change. Right, so coming back to that point about the ice volumes in Greenland, if that ice sheet melts fast, and it could, geological processes, it's going to drive relative sea level rise, global sea level rise rates rather, that could well be something like what we observed at the end of the last ice age. Okay. All right. So basically what I've just said, the ice sheets become unstable, big magnitudes of sea level rise. And to say that it's catastrophic for many cities in low-lying countries, it sounds like scaremongering, but honestly, I think that's probably going to happen to some degree in the next 100 years or so if we're not really careful with what we, how we modify our behaviors, burning of fossil fuels and so on. And it would definitely not be good news for low-lying cities. So just to summarize that bit, global sea level change has varied significantly over geological time. It was a lot higher during the late Cretaceous, as you could see from some of these sea level curves. Ice volume changes drive the fastest sea level change. Collapsing ice sheets could be catastrophic for, human cities, could cause us a lot of problems. Now, finally then, is global sea level change the only thing that's going on? I've already said relative sea level change is significant. So let's just talk about that to finish off. And there is a cat in a Pringles carton. I mean, I presume it got in there by choice, but I sometimes feel the same way actually about Pringles, I have to say. So tilted continents, isostasy and relative sea level change. It's going to finish off. So isostasy is essentially how the relatively less dense, more buoyant lithosphere crust floats on top of a viscous asthenosphere underneath, right? And like icebergs, it has to be in balance or equilibrium, so it floats. And that means if you remove some mass from the surface of the Earth, you're going to get some uplift as the floating level changes to compensate. That's the essence of what isostasy is all about, all right? And there's two different types, two different models, if you like, and probably the truth of how most situations are is some combination of these two different models, both density and variable density, uniform thickness, uniform density, variable thickness. It's probably both things are varying actually, right? And we can also actually observe that the crust behaves not just like discrete vertical blocks, but behaves more like a bookshelf loaded under a pile of books. It bends and flexes. So when you put an ice sheet on top of it, you'll get subsidence here, a bit of uplift over here, and this is what we refer to as flexural isostasy. And we can also actually say something about the time this takes. We know that when you remove an ice sheet from an area, it takes about 60,000 years for the rebound effect to occur. So you're removing a load, and so the crust underneath where the load was will respond by trying to float higher. That uplift takes about 60,000 years, but in fact, most of the uplift happens in about 10,000 years. This is like an exponential decay in the rate of uplift, all right? So if we're talking about uplift, we're talking about relative sea level change. So isostasy is one of the ways that we can actually drive relative sea level change. And as ice has been removed off the UK, there's been an isostatic rebound. Basically means Scotland is going up and England is going down. Okay, could probably make comments about Scottish independence and so on, but that would be probably a bit political. Shouldn't do that really on a Wednesday evening. So Scotland is going up, Southeast England is going down because of isostasy, right? So the removal of ice is causing rebound, and we can see evidence of relative sea level fall across large parts of Scotland. We can see evidence that relative sea level is rising in Southeast England, from direct and indirect measurements, okay? But this isostatic effect can make measurements of global sea level change also a bit tricky. That's worth mentioning here. So remember the big uncertainties on those sea level curves? Partially, I suspect it's because of effects like this. It's hard to measure global sea level because of these kind of local isostatic effects. All right, and there's also another really interesting consequence of this. You've basically got very old rocks in northwest Britain, very young rocks relatively in southeast Britain, and it's partly, maybe mostly, a consequence of this tilting effect. But I do wonder if there's maybe some other things going on as well, if it's not just isostasy, but maybe another long wavelength tilting effect. But we'll come back, well, go on to that, what the final point to finish off the lecture. So we can observe that North America is covered by layers of sedimentary rock, right? And this is actually a little bit puzzling, in as much as the whole of North America is not just one sedimentary basin that's subsided. So there's a question really, like, how did it come to be that there's 1 to several kilometers thickness of strata over the top of a continent, when continents are generally high relative to the ocean basins? It appears that North America in the past has been flooded, partly because of high global sea level change, high sea level elevations, but that's not the whole story. What we observe is that the strata are disorganized into sequences separated by unconformities, which also indicates there's been periods of deposition and erosion. Okay, so for a long time, people were saying, oh, it's just global sea level going up and down. But there's another observation that you can make, and that is that a lot of these rocks are tilted. Okay, so it can't just be global sea level going up and down, because that doesn't tilt rocks. Okay, so there's something else happening here. And here's the sequences drawn on a chronostratigraphic diagram. If you've seen one of these before, it's a cross section, but with time on the vertical axis instead of depth. And another pretty picture of some of the rocks in Utah. So that chronostratigraphic diagram is along this cross section, and it marks these kind of yellows and reds are the sequences. These are the unconformities. So there's a bit of a question generated in this kind of pattern in the strata of North America, and I will whiz through what exactly that was. Here it is in cross section, so you can see there's a kilometer or two of strata over most of North America, even though it's a continental interior. What we think is that actually that accumulation of sedimentary rocks over most of the North American continent was probably a consequence not just of high global sea level, sometimes it was high, but it's also a consequence of tilting related to this dynamic topography effect that I mentioned earlier. So related to convection in the Earth's mantle. And the way that that basically works is causes uplift or subsidence over the Earth's surface. That varies through time as the convection in the Earth's interior goes on. If you have subduction under one side of a continent, that generates a convection cell that tends to drag the continent down over the top of the subducting slab, and that essentially tilts the continent on a wavelength of a couple of thousand kilometers. So you get lots of subsidence and relative sea level rise over here, uplift and relative sea level fall over here, and that we think is probably what creates these patterns of tilting and sequence formation through North America, right? And I did work on this years and years ago when I was a postdoc in California. Since then, other people have looked at it in quite a lot more detail, and they can actually map the subduction of the Farallon slab. That's basically what used to be the East Pacific oceanic lithosphere underneath North America. North America's then moved over the top of that, and that's caused subsidence and uplift as that movement's happened. And this is one of the things that's created those layers of rock. And we can model that. This is again modeling I did when I was a postdoc. And the takeaway point is that you get big thicknesses of rock in Western US, all tilted, all produced when related to that subduction of the Farallon slab under Western North America. So big relative sea level rises produced by this dynamic topography effect, essentially driven by mantle convection. Okay, so the takeaway point here is that we've got two real big tectonic elements that control relative sea level. Isostasy is a big effect. Mantle convection is also a big effect on it. Both can happen on quite large scales. Mantle convection and dynamic topography in particular can tilt entire continents and produce layering and records of relative sea level change on a scale of a couple of thousand kilometers, right? So it's a huge effect, and it's one that we're only really quite recently starting to understand and be able to decipher in the rock record. And if any of you have ever been to Utah and Arizona, Southwest USA, and you've seen these beautiful cross sections that are drawn for, you can buy them as souvenir posters and things in national parks like Zion and Bryce Canyon and so on. These are actually showing those tilted rocks that accumulated on the continent, driven by this large scale tilting of the North American continent. So it's a wonderful example of pop geology with actually quite a really interesting, you know, emerging science explanation. Okay, so final summary then. Sea level change, surprisingly complicated. When you go to paddle in the sea, you wouldn't necessarily expect this level of complexity to explain why you're able to paddle exactly where you're paddling. Global sea level change occurs due to several very different processes, climatic processes, tectonic processes. Some are slow, some are dangerously fast, I think, as we're going to find out increasingly. Reconstructing sea level histories back through time is tricky. Okay, we can do it and we have those records, but they're probably not the final answer to what global sea level did. A big part of the issue is that we need a stable reference frame to measure it from or against. And actually, I think, as I hope I've demonstrated, when you combine these various different effects together, it's quite difficult to get that stable reference frame. So everything ends up being relative. Relative sea level change is the kind of, you know, what we're left with in most circumstances is the only thing that we can measure. And deep earth processes have affected deep earth's deep earth processes have affected deep time sea level, that should read, and they still do affect sea level. Dynamic topography and isostatic rebound are tilting continents and causing some of these effects that we observe. And then finally, I think it's probably important to say melting ice sheets are bad news, not fake news. And to finish off with is my favorite cat picture, which I think if you have cats, I think that just about sums them up. So I will stop there. And if you've got any questions, I'd be happy to try and answer them.
Well, Pete, that was a fascinating talk and took us to places which at the start I never thought we would get to. I'm sure it's generated a lot of thought amongst our audience tonight, and there'll be questions for you. So if anybody has any questions they'd like to ask Pete, if you could unmute. We have in other lectures used the raised hand option at the bottom of the screen if you want to do that, or just ask your question and be the first one to come up. So is there anybody who'd like to begin?
Chris is
Chris,
right.
yeah, you need to unmute, Chris.
Oh,
right, that's great. Go ahead.
There you go. So I'm trying to unmute you, Chris, sorry.
There you go,
right.
Chris.
I'm unmuted. I don't have a question, but I do have a comment. And the comment is that I did say to Richard that I thought I would really, really struggle to understand it. And I kind of do it by how many words I've understood. You know, 1 in 3 is pretty bad. But I think this might have been a 2 out of 3, you know, so so very good. And I think you presented what I was expecting and knew would be really quite complicated information in a very accessible way. And I love the cats. So thank you very much for that. And I shall leave it to others to ask more scientific questions or make more scientific comments.
You can't go wrong with that. That's, you know, and I mean, it's interesting. You know, I don't think there is anything in here that is actually super complicated if you can take the time to really talk through it and explain it. But I think there's quite a lot to get through, so it's hard. You know, we could break it down into probably like 3 or 4 different talks and go through it at a sort of more you know, slower speed, and then I think it might be a bit more obvious, because none of it really is truly complicated. It's not like quantum mechanics. That's what I always tell students. That's complicated.
So, Pete, can I take you back to 1988?
I remember it, Clive. Yes, go on.
In those days, I used to talk about continental freeboard and how it hasn't changed much through time. I guess basically you'd say, well, that was a silly thing to talk about because you can't quantify it.
Um,
Talking about going back
well,
to 3 gig years.
people, you know, there's, have you ever come across hypsometric curves?
Yes, yeah,
So people reconstruct those, and they use, I think they use plate models now to try and reconstruct them, right?
Yeah.
So I think, yeah, I mean, I think that dynamic topography effect probably means that it has, those hypsometric curves have changed quite a bit through time on certain continents, I suspect, if that's what you mean.
Well, basically, it was rate of continental crustal growth.
Oh, I see. Right. Yeah.
Yes.
Well,
dragging back memories.
so yeah, I don't know. I don't know about continental crust. I mean, I'm not sure how much. So the effects that we're talking about there on ocean volume, I think the spreading rate is probably a bigger control on a shorter time scale than the continental area would be, isn't it? I think that's probably the case.
Yeah, I think using the freeboard is probably a bit silly.
Right.
I don't want to hog discussion, but if there's nobody else,
Oh yeah, please.
oh, right, go, Mike.
I thought there was a time when Lake Agassiz lifted the ice up in Hudson Bay and all the water escaped into the Atlantic, raising sea level by 2 meters over a period of maybe 2 or 3 years. Is that no longer thought to be the case?
So where was this? Sorry.
In Canada, Lake Agassiz, I think that's the name of the lake.
Right.
And that was blocked from draining into the sea by a huge block of ice in Hudson Bay. And eventually, the water got underneath that ice and lifted it up, and all the lake drained into the Atlantic.
Right. Yeah, I mean, I think there's been a few events like that in areas around the North Atlantic over that period of deglaciation, and they've had quite a dramatic effect. I don't know about the magnitude of sea level rise that they've driven, but I think there are ideas that they seriously impacted on the thermohaline circulation, you know, the Gulf Stream, basically, because you had big influxes of cold fresh water into the North Atlantic, and it really changed the circulation patterns, at least for a time, and that in turn disrupted climate. And you can pick up those signals in warming and cooling intervals that are happening on a much faster scale than the overall deglaciation. So yeah, things like that definitely happened. And I mean, there are much smaller examples of similar things in the UK, aren't there? So if you've ever been to Ingleton, the valley there was supposedly cut by a big glacial outwash event that was breaching of a terminal moraine and so on, with a big lake behind it. So I think things like that have happened quite frequently. But I don't know about the actual 2 meters sea level change. I don't know.
Okay, probably an exaggeration I read somewhere. Thank you
Well,
very much.
Yeah, 2 meters, that would be an awful lot of water. So I don't know whether, I mean, I think you probably have to drain a lot of water out from underneath the whole ice sheet for that to happen, but maybe it's possible.
Okay, thank you.
Thanks, Mike. Pete, there's a question from, is it Gis Southworth? If you want mute.
Yeah.
Somebody's got
Can you hear me?
Yeah.
Yeah.
Yeah, we can hear you.
Yeah, Pete, it's about the image you showed of the British Isles, where Scotland was rising and southern England was sinking. Obviously, we've always been taught that was due to the isostatic uplift after the ice sheets melted. So what fascinated me was the suggestion that it's a much longer term tilting process that might be taking place. I wonder if there's any other examples of that sort of thing taking place worldwide, because it really sort of stuck a note with me.
So the reason I said that is, well, I wonder if it was just an ice related tectonic effect, whether, I don't know, it just seems like a lot of erosion down to those kind of crustal levels in northwest Scotland for that to be the case. But I don't know. I've never really tried to look into it further. But one thing that could cause at least some of the uplift is, I don't know whether you ever heard of Iceland Plume. You know, there's supposed to be a mantle, well, there is a mantle plume underneath Iceland.
Yeah.
And one consequence of that is that area of the North Atlantic is elevated by dynamic topography, we think. And if, you know, you don't have to extend that dynamic topography too far before you get into northwest Scotland, and you can imagine how that tilting then might be related to that kind of related dynamic topography process.
Yeah.
So, you know, it just makes me think it's rare in geology, and I don't know, maybe Clive will have an opinion about this, but it's rare in geology and tectonics that things happen for just one reason. There's usually more than one thing going on, and I wonder in that case whether it's another example. You know, it's not just isostatic control.
Yeah, and that was something sort of that made a connection in my own mind as you discussed dynamic topography as well. There must be some link out. It seems to be somewhat too much of a coincidence, I would probably put it as, but it's fascinating. Thanks.
But I mean, it'd be great to have a PhD student work on it actually, and see. I'm not quite sure how you would investigate it further, but it'd be interesting to think about ways to work out, you know, whether ice sheet removal and isostatic rebound could account for the whole effect, or whether you do need something else.
Yeah, it's a big project by the sound of it.
Pete, there was a lecture recently by Nicky White.
Oh yeah.
Talking about his work related to the Iceland Plume, and in his modeling he has several large lateral fingers that extend from the plume, and he argued that the only reason the British Isles actually exists as a land area is because of one of these fingers. Because he said if you look regionally, you have the same rocks that are in most of southern England are actually buried to significant depths, both in the west of Ireland and in the North Sea basin. So why is there this finger of land called Great Britain? And he gave a very convincing presentation related to one of the fingers from his mantle plume, which he's published. And I did check out the paper, but there was a huge difference between his very interesting presentation to the pages and pages of mathematics, which I just couldn't get into in this paper. But he's done a lot of work related to this phenomena.
Okay. So when I worked on dynamic topography back in the late 1990s, Nicky was deeply skeptical of it, and I once went and did a talk at Cambridge, and he and Dan Mackenzie gave me a right grilling. I was like a toasted cheese sandwich after they'd finished. Oof. And they were both like, "Oh no, that can't possibly happen." So it's quite funny now that Nicky has become such a vocal proponent of the process. I must, next time I meet him, I'm gonna have to say to him, "Do you remember, Nicky, when you didn't believe in this?" But you know, I mean, I think it over time the evidence has just become a bit more persuasive. But that's interesting, Richard. I didn't know about that work. I'll definitely check that out. What's the title of the paper? Like Nicky White's Great Big Fingers. I'll have
to check my notes. I'm just looking now, but I can't find where I've scribbled it down. I mean,
this is the beauty of Google, isn't it? I can probably find it quite easily if I search for it.
Yeah, yeah. So I think we have a question from John Wood.
Thank you, Richard. Just actually thinking about this isostatic rebound again, you said that most of that, the highest proportion of that happens fairly early on, and then slows down. I just wondered how much more is there left for Scotland and possibly northwest England?
Well, yeah, that's a good question. So I'm trying to remember what the proportion is. I don't know. We'd have to check. I think to keep, yeah, I couldn't be more precise than to say most of it has happened, but not all of it. So I don't know, 70-80% perhaps. But I think that uplift pattern is probably going to persist for another, 10-20,000 years, I would guess. But it's just going to get slower and slower over that time period. So most, but not all. I mean, we could look it up in a textbook, I think, and you could probably answer that question a bit more precisely. But that I think is the answer.
Okay, thank you.
It's just going back to that plume discussion piece. I mean, I can recall reading papers relating uplift in the Paleocene times.
Yeah.
Resulting in huge erosion in the Highlands of Scotland to provide the source material for the thick sort of Paleocene, Eocene sandstones you get in the North Sea basin.
Yeah, I think indeed, and there's offshore examples of that. I've not seen anybody actually link that though to the much more regional, bigger sort of several 100-kilometer pattern from northwest Scotland down to southeast England. But I suspect that is a part of the story. And the fact that there was these big episodes of Paleocene erosion would definitely fit with that, wouldn't it?
It would, yeah. 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 So, anybody else have any questions for Pete? No, I think.
Just to say thank you very much. It was very interesting.
Thank you, Mike. You're welcome.
Yeah. Okay. Well, I would like to invite John Wood to come forward and give a vote of thanks on behalf of Westmoreland Geological Society, Pete, for an excellent talk. A great way to spend a Wednesday evening listening about dynamic topography. Can't beat it.
No.
John.
Yeah, thank you very much indeed, Pete. It's been a fascinating talk. Very interesting to have all those definitions at the beginning of the different sorts of sea change, the relative and the global. Found all that as a mathematician very interesting, some of the definitions near the start. I hadn't actually realized, I have to say, there are quite so many things that could lead to the global and local sea changes. So it was very interesting to hear about all of those. I particularly found the section about the seismic record and looking at that with the sedimentary record very interesting. So lots of interesting things in there. I hadn't realized there was so much uncertainty when looking back at what sea levels might have been in the past. I suppose naively, having read various things, and you tend to perhaps read one thing in some magazine somewhere and think, that was the sea level back in the Cretaceous or whatever, to realize that the models were so hugely variable when you saw them. So that was very interesting indeed. Very pleased to hear the answer to my question that we still have a bit of upwards to go, hopefully in the northwest as well as Scotland. And I'm pleased because I was very worried that the Anthony Gormley sculptures were going to disappear under the sea in Crosby. So perhaps he's gotten the right height after all. Just one final thing I'd like to say. I was looking you up a little bit earlier this afternoon and seeing one or two things about you. Members might like to have a look. That one of the things that Pete looks after is the website, I believe, of the University Geosciences UK. Your Liverpool University site says that you're responsible for some of that. Fascinating website to look at.
Yeah, I mean it's So I've really just put together material from lots of other science departments, but I mean, in summary, we wanted a website where prospective earth science undergraduate students could go and look and see what the subject is all about and why it's relevant to them, you know, why they should come and study earth science and pursue a career in it. So that's its purpose. And
do have a look at it if people haven't. There is a fantastic video about what is in a smartphone, and it's great.
Good, isn't it?
I think all teenagers should look at it and actually try it themselves, because you start by putting your smartphone in a blender and then analysing all the various bits you get out. So it's quite fascinating. So do
if any of you actually have teenagers, you probably wish they would, right?
Exactly. So thank you very much indeed, Pete. Excellent tour, and enjoyed it very much. Thank you. Can we show our usual appreciation?
Well, thank you very much. It's a real treat to be able to talk about this to an audience. So I really appreciate you taking the time to watch. It's really great. Thank you.
Thank you.
Yeah, thank you, Pete. That was good. Yeah. I just got one more announcement before I just leave the room open for people to have a chat. And that's, we have one more lecture this winter season on the 24th of April. And it's one of your colleagues, Pete, Richard Warden, is going to talk to us.
I didn't know that. Okay, cool.
He's going to give his lecture on the geology of carbon capture and storage. So quite a topical talk this current time, with the big projects being announced in Norway and the slightly smaller one for Teesside in the offing. So yeah, that's on the 21st of April.
Cool, that'll be good.
So I will, yeah. So I'll leave the room open as long as people want it to socialize as much as you can with a screen. And yeah, and I'll just say thanks and a lot, Pete. That was a really good talk.
Cool, thank you.
Thank you very much.
Yeah.
Thank you. Thank you very much.
Bye.
Thank you.
Pete, are you doing